Hello, I'm Charlie Bryant, and this is Lab 3, Black Holes Orbit. Our objective is, using a given set of positional data of an observed star over time, calculate the mass of the black hole around which the star orbits. Our process: by calculating the change in momentum of the star, dp/dt, through computational iteration, we can use the momentum principle in relation to Newton's law of gravitation to then determine the mass of the black hole. Here are the physics principles involved. First off, we have the momentum principle, which is a derivation from Newton's second law that tells us that the change in momentum, final minus the initial, over time is equal to the net force. I'll now demonstrate how we computationally calculate the change in momentum. The initial and final velocity are derived from the experimental data. Then, multiplying by the star's mass, we obtain an initial and final momentum. The change in momentum is found by simply subtracting the initial from the final. Lastly, dividing by our time step, in this case the number of seconds in a day, we end up with the net force. Next up is Newton's law of gravitation, which states that the force due to gravity between two entities is the universal gravitational constant g times each of the entities' masses divided by the distance between them squared. In this case, we will assume that this is the only force acting upon the object and is thus our net force. We can then algebraically deduce the mass of a black hole, as shown in the last line of the code below. I'll now run the code that simulates what we just discussed, and it'll print out the value of the mass of the black hole, which turns out to be about 2.985 times 10 to the 31st, which is roughly equivalent to 10 times the mass of our Sun. So what does this mean? We know that the change in momentum can be broken down into its parallel and perpendicular component parts, which correspond in turn to the parallel and perpendicular parts of the net force. As demonstrated in the code here at the bottom, the parallel component of the change in momentum is equal to the change in magnitude over the change in time times the unit vector in the p direction, where p is our initial momentum. We can then find the perpendicular component simply by subtracting our results from dp/dt. Now we'll run the code again to visualize the force. The yellow arrow is the net force, which will always point directly at the location of the black hole. The blue is the perpendicular, and the black is the parallel. Notice how the arrows grew larger as they were moving towards the black hole and grew smaller as they moved away from it. So how do dp/dt and fnet relate to one another? Well, the change in momentum is found from observational data, taking our final minus our initial, whereas fnet is really just a concept. The change in momentum is the ending result, and fnet is the means by which the momentum is changed. And really, fnet is only truly equal to the change in momentum when dt is infinitely small. Now, what if we replace the black hole with another black hole and the star's motion remained unchanged? Could this black hole have a different mass than the original? Well, let's look at our equation. Since the motion remained unchanged, the positional difference between the star and the black hole will stay the same. So, our old radius and our new radius will be the same, and therefore the old net force and the new net force will be the same. And if the net force remains the same, the only way that this equation can hold true is if the mass of the old black hole is equal to the mass of the new black hole. Thus, the masses must be the same as before.